All right, so we're going to talk about section 3.1 today. It's on quadratic functions and quadratic vertices. Uh, and so it's going to be a little different than Module 1 because in Module 1 we were mostly dealing with linear equations, right? And those are useful in some scenarios, but not in very many, honestly, because things don't always, just behave linearly. They don't always increase at the same speed. They don't have that constant slope all the time. So we need to be able to deal with scenarios where things are changing over time. Okay, so quadratic functions is going to be our first step into that, and we're going to wind up with some graphs that look like this, some U-shaped graphs, right? Where we decrease for a while, hit that bottom point, and then start increasing, or like this, where we increase for a while and then decrease after we hit that peak there. Okay, so we're going to be able to deal with some things that have a slope that's changing over time. Okay, and so to do that, we need to understand how quadratic functions work. So we're going to start by talking about quadratic functions that are in standard form. Okay, and this is what that equation looks like. F of x equals ax squared plus bx plus c. And you'll note here, a can't be 0. We have to have the x squared term or we're not looking at a quadratic function. Okay, so uh, a few examples of what these quadratic functions might look like. Now, you note here that a can't be 0, but b or c can. So we don't necessarily have to have all three terms in order to have a quadratic function, but we can. So a few examples of things that are quadratic. You could have something like 3x squared plus 2x minus 7. That's certainly a quadratic function. Or uh, negative x squared plus 5. You'll notice I'm missing this x term. That's okay because that just means my b value is equal to 0. We're missing that term because the coefficient of it is 0. So this is still a quadratic function because we have that x squared term. Okay, so these are quadratic. Okay, let's look at a couple of examples of things that are not quadratic. Well, the linear equations, if we're missing that x squared term, if we have something like, 3x plus 7 that we saw in the last one, that's a linear equation. The graph's going to be a straight line. It's not going to give us one of these U-shaped curves like we saw in the example earlier. Okay. Also, if you have a power that's bigger than 2, like 3x cubed minus 2x plus 7. This is also not quadratic. Okay? This is what we call a cubic equation, and we'll deal with these later in the course. But our biggest power on one of our variables needs to be a power of 2 in order for us to have a quadratic function. And then if we do, every single one of these quadratic functions is going to give us a U-shaped graph that looks like one of these two. Okay? And we know a little bit about which one of these two graphs it's going to look like just based on some of the values in the standard form equation. So let's talk about that a little bit. The key is going to be our a value, this x squared coefficient. It's going to tell us a lot about what our graph is going to look like. So let's discuss that. So if our a value is positive, bigger than 0. Okay, so 2, 3, 5, 7.5, whatever. Any number that's bigger than 0, okay, then our parabola is always going to open up. Okay, so we'll have a graph that looks something like this. Okay, a U-shaped graph that opens upward. Okay, and we talked a little bit about concavity in Module 1. Okay, one of the things about quadratic equations is that their concavity is always the same. So a graph that opens up is always concave up. Okay, and if you recall back in Module 1, we talked about concavity. The easy way to recognize what kind of concavity you look like is does the graph hold water or not? So in this case, you put water in it, it's going to hold it like a cup. So the graph is always concave up. Okay, similarly, if our A is negative, okay, then our graph is going to open down instead. And so our U-shaped graph is going to look something like this. Okay, and also similarly, this would not hold water, right? This would dump water out. So it is a graph that is concave down. All parabolas will not ever change their concavity. We'll certainly see graphs later in the course where we have parts of the graph that are concave up and parts of the graph that are concave down within the same graph. That will not be the case for quadratic functions. They're either always concave up or always concave down. Another thing that we can get directly from this equation is the y-intercept for the graph. So if you recall from Module 1, the y-intercept is the point where our graph crosses the y-axis. And every y-intercept has one thing in common: x is equal to 0. And so if we plug 0 into this equation, all of the pieces that have x's in them, this one and this one in particular, are going to go to 0, right? So if we plug 0 into this equation, we're going to get 0 plus c, or c. So our y-intercept at every one of these quadratic functions that are written in standard form is going to be the point 0 and c. It's going to be this constant value on the end that tells us where that y-intercept is. So quick and easy to recognize where your y-intercept is when you're in a situation where you have a quadratic function in standard form. Okay, so let's look at a few of these quadratic equations in Desmos just so we can see what's going on. So here we have the first one, fairly straightforward. We've got a quadratic equation in standard form. We have all three terms here, right? Our a value is a 1, which is a positive number. So I know just from looking at this equation that this is going to be a U-shaped graph that opens up. Our a value here is positive, and I also know that my y-intercept is going to be 0 and 1. We can just read it right off of that constant value at the end there. So we know a lot about what this curve is going to look like just from looking at this graph. So let's turn it on and see what happens. Okay, you'll notice it opens up because our a value was positive, and it goes through that y-intercept value of 0, 1. Okay, one thing that's different about these quadratic curves compared to the linear curves we had before, when we had a straight line, the most that could ever cross the x-axis is 1 time. But with these quadratic functions, it's possible for us to have up to 2 x-intercepts, right? In this case, we certainly do cross the x-axis twice, so there's going to be 2 zeros or x-intercepts for this particular curve. So that's something to keep in mind. Okay, let's look at the next one. Again, this is another quadratic equation in standard form. You'll notice we're missing that x term. That's okay. It just means our b value is equal to 0. Okay, so this one, though, we know it's going to open down because we have this negative in the front, and we know the y-intercept is going to be at 0, 4, because that's what our constant value is on the end. So if we take a look at it, that's what we see. We see it go through that point 0, 4 up there. And then we see that it opens down because our a value is negative, and then our x-intercepts are -2 and 2 here. But it does cross the x-axis twice. Now, they won't always cross the x-axis twice. Let's look at an example where that doesn't happen. Okay, so this next one, again, we see the equation that's in standard form. We see that this one's going to open up because our a value is positive, and we see that it's going to go through the point 0, 2. That's going to be our y-intercept because that's the 2 on the end there. If we look at our graph, though, it's going to look something like this. So again, it goes through that point 0, 2, opens up, so everything we expected to happen happened, right? But this one just doesn't cross the x-axis. So there's this is certainly a situation where we have a parabola that doesn't cross the x-axis. And so that's a possibility as well. Now, there's actually 3 cases that we can run into when we're talking about the roots or the zeros of a function like this. Let's look at this last one. It's very similar. This one's going to go through the point 0, 4 for the y-intercept, and it's going to open up. But watch what happens when I graph this one. Okay, it's going to be a point over here where it comes down and it touches the x-axis and then turns around right away. Okay, so those are the 3 cases for the zeros that we're going to have when we're dealing with a quadratic function. We can either have 2 zeros, like this one where our graph crosses the x-axis twice. We can have no zeros in a situation like this where our graph just never crosses the x-axis. And then we can have 1 0 when our curve comes down, touches, and turns on that x-axis. So we just have that 1 point where it hits the x-axis. Okay, so those are the 3 different possibilities. Section 3.2 is going to be all about the zeros of these quadratic functions. So we'll talk about that in more detail a little later. Okay, so let's talk a little bit more about the most important point that is on these quadratic graphs, and that is, the bottom of the valley point in a curve that opens upwards, or the top of the hill point in a parabola that opens downwards. Okay, now these are important because usually when we have graphs like this, we're trying to optimize them, right? We're trying to find the most efficient way to do something, right? And so, like, think of this like a cost curve, right? The lower you are, the lower your costs are, and we want to minimize our costs at a lot of places. So we're going to be very interested in finding that bottom of the valley point, because that's going to be the point where our costs are minimized in a scenario like that. Similarly, over here, if this is like a profit curve or something, well, guess what? Every company wants to do. They want to maximize their profits, and the point of maximum profit is going to be that top of the hill point there. Okay, we call these, they have a lot of names. Sometimes we call them critical points. We'll call this a minimum. We'll call this a maximum. Okay, but for parabola, we're only going to have one of these turning points in our graph, right? And for this particular type of equation, we're going to call that the vertex of the parabola. Okay, so these are very, very important for us to be able to find, because they're important for decision makings when we have models like this. Okay, and we can find them by hand, and it's actually not too bad. Okay, so let's talk about the way that we're going to calculate the vertex by hand. And you'll certainly have to do at least one of these by hand on the exam. Desmos is also excellent at finding them too, so it's a very easy thing to check your answer on. But if you want to find them by hand, all we're going to do is we're going to use this particular equation. X equals minus B over 2a. So these values that come from our equation will be used to calculate the x value of our vertex. Okay, once we have that, then we're going to take this answer that we get here and we're going to plug it into, to find the y, we're going to plug that value in to our function. Okay, and that'll give us our y value that goes with it. So our vertex is going to be at minus b over 2a and f of minus b over 2a. And I know this looks a little complicated, but it's actually a lot more straightforward. This makes it appear. Let me show you how it works. So let's say we have a quadratic equation that looks something like this. Okay, I want to find the vertex for this particular quadratic equation. The first thing I need to be able to do is recognize what my a, b, and c values are. Don't really need the c for this, but we'll write it down anyway. So our a value is our x squared coefficient. So in this case, our a is 1. Our b is our x coefficient, so that's 4. And then our c is our constant coefficient. We will need all these values for a formula that we use a little later, but so we'll just write them all down. Get in the good habit there. Okay, so to calculate the x coordinate of the vertex, I'm just going to plug these values into this little equation. So on the top, I think of this as the opposite of b. So whatever my b is, I'm just going to take its opposite. I'm going to change its sign. So that's going to be negative 4 over 2 times a, which is 1, right? And then I'll just work that out and get negative 2. Okay, so that's the x value of our vertex. To get the y value, all I'm going to do is I'm going to take my function and I'm going to plug the answer I just got into it. Okay, so I'm just going to plug that negative 2 in for x in our equation. And if you're going to put this in a calculator, don't forget to put that negative 2 in parentheses. You will get the wrong answer if you don't. Okay, so this is 4 minus 8 plus 5, so that's negative 4 plus 5 is going to give me a 1. So my vertex for this particular parabola is going to be at negative 2 and 1. And because this opens up, I know that this is a minimum point. It's going to be like the bottom of the valley because this opens up, because our A value is positive. Okay, let's do one more. So let's say we have something like this. Okay, so this is a good example to show that it's not the order that is important in how we write this, right? It's what kind of term this number is in front of, right? And our A is written first here. It doesn't matter if it's written first. What determines what A is what the number that's on the x squared is going to be our A value, right? So in this case, my A value is going to be negative 3, the value in front of the x squared. Then my B is going to be the coefficient of the x term, so my B is going to be 12. And my C is the constant value. In this case, we don't have a constant value, so our C value would be 0 there. So it doesn't matter what order they write them in. We just want to make sure we're kind of matching these things up. I guess one quick note while we're here, this is certainly going to be one of the notes I put on the board when we take our Module 2 exam. So make sure you don't have to memorize it. You just need to know how to use it. You'll have it available to you when you take your test. Okay, so get back to this problem. Let's get our values. So my A, again, is my x squared coefficient. So that's the negative 3 there. Our B is our x coefficient. That's the 12. And then our C is our constant coefficient. We don't have one. So our C value is 0. And that's totally fine. It's the only value that can be 0 if we want to have a quadratic is our A. Okay, so again, if we want to calculate this by hand, we're going to plug into our formula here. So we want the opposite of B over 2 times A. So the opposite of 12 is negative 12 over 2 times A, which is negative 3. Gives us negative 12 over negative 6, which is positive 2. And again, that is the x value of my vertex. To get the y that goes with it, all I'm going to do is I'm going to take this x value, I'm going to plug it in for x in my original equation. So I'm just going to do 12 times 2 minus 3 times 2 squared, plugging the 2 into those values. So this is 24 minus, that's 4 times 3 is 12. So our vertex is at 212. Now, don't forget that Desmos is excellent at finding these vertex points, these critical points on our graph, right? So if you ever want to check this, just put this graph into Desmos, just click on the, this one's going to open down since our A is negative. Click on that top of the hill point and it'll find it for you. You can check your work quite easily there. Just remember that you will have to do at least one of these by hand on the exam. So you want to make sure you practice that a little bit. Okay, so we are certainly going to be dealing with some application problems that involve these quadratic equations. So we'll look at some of those. So let's say that this particular equation models the population of a small town in thousands of people where X is the number of years after 1950. Okay, so we want to find the vertex and then we want to interpret it in the context of the problem. And you know we're going to 100% have several interpretation problems on the exam. Math doesn't really matter unless you can tell me what that answer means in context. Okay, so the first thing that jumps out at me about this problem is that we've got a bunch of decimals up here, right? So that is a hint to me that we're probably going to want to use Desmos for this particular problem. So that's going to be my first step to working this out, is take this and I'm going to put it into Desmos. Okay, and so I've already done that, but you'll notice when I do it and I have it on a standard window, I can't see anything right there, right? So I need to kind of adjust my window. It makes sense because our y-intercept, if we look at that, is going to be, almost 6,000, right? We only see through 0 to 10. So our y values are kind of useless here. So we're definitely going to have to play with our window here a little bit if we want to get a good graph of this. So my x value here is the number of years after 1950. So I'm assuming that that first value is 0, right? And then it's 2026, right? So 2026 minus 1950 would be 76. So I'm going to go ahead and try that as an X max. This, of course, is a guess and check process, right? So this 76, I just went to the present day. Might be good, might have to adjust. We'll have to see. But my Y values here, okay, the first thing I know is that we're measuring the population of a town. No such thing as a negative population, so I'll start here at 0. And then I know that the y-intercept is at this 5790.99 value. And I know that this problem is going to open down, right? So my maximum is going to be higher than this. So I'm just going to kind of guess and check some values until I find something that's going to work for me. So maybe I try something like, I don't know, 7,000, something a little bit more than that 5790. Okay, and that does give me the curve. Okay, but again, this is where I want to adjust. I want to note that I am not using anything from here all the way down to the bottom of the screen, right? None of this is any value to me. So if I want to get a better picture for what this parabola looks like, I'm just going to kind of zoom in on this part of the graph, like 5,000 to 7,000 is probably good enough. Whoops. So let's just pop in here. Let's change our Y values here to 5,000 to 7,000, and I'll have a better picture for what's going on. I can see that U-shaped curve that I expected. Okay, and again, I didn't do anything wrong there. I didn't get the window exactly with the way I wanted it the first time. That's okay. That's part of the process, right? We're guessing and checking a little bit here until we get a good picture for what's going on. Now we're asked to find the vertex. Let's say we want to round to the nearest whole number on both of these. Okay, so my vertex is going to be at 57 and 6870. Okay, so we've got our vertex. So now the second part of the question is to interpret that. Let's go back to the screen. Okay, so remember first off what our X is. X is our number of years after 1950, right? So if we do 1950 plus 57, that means we are in 2007. Okay, we're measuring the population of this town is 6870. Don't forget to pay attention to the scale of the Y units on the problem. So this is 6,870,000 people. This would be one way to write it. I would count this correct. It's a little weird. Nobody would usually say that. What we would do instead is we would just write it and then we would add the 3 zeros to show that it's in thousands. Okay. So in 2007, the population is 6,870,000 people. Maybe throw the word about in there. Okay. Another thing that you want to make sure you're paying attention to here is what we're finding is the maximum population, right? So you could say the maximum population of the town is 6,870,000 people, and it reaches that in 2007. That would be a fine interpretation as well. But this is the most people that will ever be in this town according to this model. Okay, so in module 1, we saw a problem that was similar to this. We were standing on top of a building. We throw a ball up into the air, right? And it goes up for a while, hits that peak, and then comes back down. And again, if we ignore air resistance, then this is going to perform exactly like a quadratic equation. Gravity performs like a quadratic equation in a lot of cases. And so they give us a model for this, right? The height is in meters for this one, and it says our t value is in seconds after the ball is thrown. Okay, so let's find the time at which the ball reaches its maximum height. Okay, and the ball is going to reach its maximum height at its vertex. Now, we did this problem in module 1, And if you recall, I told you we just didn't have the tools to solve this by hand. Well, now we do, and our numbers are actually going to be reasonable to work with here. So let's go ahead and do this one by hand just to get a little extra practice with that. Okay, so in this case, we're trying to find the time at which the ball reaches its maximum height. Well, time is our t value. It's in our x position this time. So we're looking for a t. If we want to find when that happens at the vertex, we're going to use our vertex formula. Our t is going to be minus b over 2a. Okay, and we have to pay attention. Again, these are not in the order as the same order as the standard form equation that I gave you, but this is my a because it's on the squared term, right? This is my b because it's on the t term, and then this is our constant term, so that's our c value. Okay, so when we go to plug into this equation, we want the opposite of b. The opposite of 19.6 is negative 19.6, okay, over 2 times a, which is negative 4.9. Okay, if you throw this in your calculator, that's negative 19.6 over negative 9.8. That will give you 2 there. Okay, so the answer to this question is the ball will reach its maximum height after 2 seconds. Okay, then I might ask you the next question, what is the maximum height? Okay, if I want to do that, I'm just going to take this 2, I'm going to plug it back into this equation over here. 4t. Okay, I'll go throw that into Desmos real quick over here, and we'll see what we get. Two squared's 4, so I'll just throw that in like that. So I would get so I would get 54.6 here. And again, pay attention to your units. Whoops, let me switch back. So in this case, my units are in meters, so this is our height in meters. So if I wanted to interpret what the vertex means in the context of the problem, I would say something like the ball reaches its maximum height of 54.6 meters after 2 seconds. Okay, make sure you get the x value in its units, the y value in its units on there when you're doing an interpretation. Okay, so hopefully that's helpful and enough to get you started on 3.1. Again, I'll be around all week, so if you have any questions, feel free to send me an email or use the Ask My Instructor button in my math lab, and I'll be happy to help with any questions you might have. Y'all have a good day, and I'll be back with 3.2 in a little bit.